Welcome to Fundamentals of Computers lecture series. In this session, we will talk of logic gates and the processor circuits, specifically the adder circuit. The objectives of this session are to cover logic operations, also referred to as logic gates, how the logic gates are represented through electronic circuits. We will specifically look at AND gate as well as OR gate. Arithmetic operations using logic gates. Specifically, we will look at the adder circuit that can be constructed using the logic gates. And finally, we will have a look at the computer in a bigger picture, and then specifically look at some of the components of the computer that are more important and that we'll be talking of in the next session. As a reminder, in the last session, we talked of binary numbering system. In this numbering system, we had we talked of the two digits that exist in the binary numbering system, and these two digits are 0 and 1. And we talked of different operations that are possible on these numbering systems. We also discussed the conversion. We talked of hexadecimal numbering system, and then we talked of conversion between binary numbers and hexadecimal numbers, where we saw that 4 bits combined together can be converted into an equivalent hexadecimal number. And that way, arbitrary number of binary bits can be converted into equivalent hexadecimal number. And we talked of why this is important. We looked at some of the operations that are possible on the binary numbers. We did not go through a lot of details, but the objective was to actually show that the operations on the binary numbers are roughly equivalent to the operations on the commonly used decimal numbering system. Finally, we had a look at ASCII chart, which was designed to standardize the representation of different character sets and characters in binary numbering system. In this session, we are going to pick from this point onwards and talk of the logic operations, and then we will see how the arithmetic operations can be represented using logic operations. So let's start with the logic gates or logic operations. In the last session, we talked of 4 logic operations, namely AND, OR, NOT, and exclusive OR. I explained the truth table of these 4 logic operations in the previous session. In this session, we are going to add 4 more logic operations, which are NAND, NOR, buffer, and exclusive NOR. So I am not going to cover a lot of details of these operations, but just to give you a quick idea of the NAND operation is actually the reverse of AND operation. So if you look at the truth table for NAND operation, notice that wherever a result of 1 is generated in case of AND, the NAND generates the reverse of that result. Okay, so the NAND operation between 2 bits that are 1, that produces the result of 0. In all other cases, the result is 1. A simple way of understanding the NAND operation is actually having the AND operation and then after that performing a NOT operation. So you notice that in the NOT operation, we convert 1s into 0s and 0s into 1. So if we apply a NOT operation here, okay, what will we get? We will get a value of 0. Similarly, NOT of this 0 will be 1, 1, and 1. And this is our NAND operation. Similarly, the reverse or NOT of OR is a NOR operation. The reverse of buffer, the reverse of NOT is buffer operation. Buffer is just forwarding whatever value is received, that value is forwarded. Buffers in general are also called as storage units, and they are also known as flip-flops. One of the forms of the buffers is flip-flop, but there can be other forms that exist. They generally store the values in the systems. And the reverse of not or reverse of exclusive or not of exclusive or is the exclusive NOR operation. Okay, so this completes the set of logical operations that are relevant to the computers. I am not going to go through all of the details, but in general, everybody should remember the equivalent truth tables and understand why the truth table is the way it is. So this is an important aspect as far as uh, understanding of the computers is concerned. All of the logic gates are represented in the computers for ease of usage. Instead of writing those textual values everywhere, the easy representation is to assign the symbols to the logic circuits, logic operations, and these circuits are the symbols and the circuits behind those symbols are referred to as logic gates. So the symbol for AND is a D with two inputs and one output. So this will be input A or X, this will be input Y or B, and this will be our result of A and B or X and Y. Okay, on the similar lines, the representation of OR is the symbol shown here, the NOT symbol. Reverse of NOT is a buffer. So notice how the NOT symbol is actually represented by a 0 mark at the end, and then look at the NAND, the symbol for NAND and AND. You will see that AND gate followed by a NOT symbol gives us NAND symbol. Similarly, OR followed by a NOT gives us NOR, and exclusive OR followed by a NOT gives us exclusive NOR symbol. So instead of writing the textual form, these gates are generally, when the diagrams are made, when the circuit diagrams are created, the symbols are used for the purpose of representation of the gates, and that makes it more easy to follow in terms of diagrams. Now, how are these logic gates created? What I want to show from this particular portion is that the logic gates and in general the computers are actually electronic circuits. Okay, they are nothing more than electronic circuits. So let's have a look at how electrical or electronic circuits can be used to create and OR gates. Okay, so here is an example. This is an electronic circuit. Those who have some understanding of the electronics, they understand what a transistor is. A transistor is a semiconductor-based electronic circuit, and they come in sizes of few millimeters to a few nanometers. So as the technology advances, the size of a transistor is becoming smaller and smaller. So here, two transistors are shown. You do not need to understand all of the details of the transistors. I will explain a basic operation of how the transistor works so that we can understand what is happening in this specific circuit. So here the voltage is applied, generally 5-volt power supply. The computers work on 5-volt. If you are familiar with your mobile phones, you see the charger is plugged into the mobile phones. That charger provides a current of 3-volt or 5-volt to the mobile phone. Similarly, the battery inside the mobile phone provides a small amount of current. So computers, general purpose computers, generally work on 5-volt supply. This is ground. So that these two points combine together. So basically, if we connect this circuit on this side, here there will be a source of power. Okay, so a wire connected to a power source. So how do the transistors work? This voltage is constantly applied at this point. Okay, however, so the transistor has three edges. This is called emitter, this is called base, and this portion of the transistor is called a collector. It's a three-leg circuit. So emitter is always connected to a power source. If we apply some power, some voltage at the base, the voltage on the emitter side is transferred to the collector side. On the other hand, if no voltage is applied to the base, then on the emitter collector side there will be no voltage. This voltage does not get the current does not flow from emitter to collector unless there is some voltage applied onto the base. Okay, so this way, if I have a zero value over here, that means I am not applying any voltage. This circuit has been open. Okay, so there is no voltage being applied on the base, and therefore we will get a value on collector will be 0. Okay, on the other hand, if I apply the value of 1 over here, which essentially means that I connect this point, a value of 1 is applied or a voltage is applied over here, then this collector will also show some voltage value which will be equal to the value of emitter, and therefore we call, whenever the current is flowing or the voltage is being measured, we say that this value is 1. Whenever the current is not flowing and voltage is not being measured, we say that this value is 0. Okay, so if the current is applied at this particular point, we say that a 1 value is being applied, and that will result in flow of the current through the transistor, and this value will become 1. Okay, so this is the basic operation of the transistors. So now let's look at how this particular circuit is an AND gate. You don't need to learn this, you don't need to understand all of this, but if you know how the computers work, what are the basic units of the computer, that actually helps you understand the working of the computer much more better. So the basic idea is that this will be, I will not say that the voltage is applied, I will say that this value is 1, always 1. Okay, here I want to perform an AND operation between the bits 1 and 1. Okay, so I want to generate this result, which means that I will apply a 1 over here and a 1 over here. Now we know that if 1 is applied over here, that will get transferred on the base, and if the current is applied at the base, this value is transferred over here, so we will get a 1 at this particular point. Okay, which means that for the second transistor, the current is being applied at the input, the voltage is being applied at the input. If this transistor works and there is a value of 1, the value will be transferred on the output portion. Otherwise, the value will not get transferred onto the output portion. So this value is also 1, which means that this 1 from here will get transferred to this point. A value of 1 will be registered here, which is our output point. We are measuring the output over here. So an output of 1 will be generated through this circuit. Now let's roll back and try to provide a different input and see what happens with that result. So I want to perform an AND operation between 1 and 0. Okay, let's see how this circuit produces that result. We have a 1 value over here. We receive a 1 over here, which is okay. Now a value of 0 is applied over here. So because of 0, this 1 received over here cannot be transferred over here, and the value over here will remain 0. Okay, so our output for this operation will be 0, which is what our AND operation is. It produces a 0 result if even one of the inputs is 0. Okay, so let's roll back a little bit more and see if we perform this operation in the reverse direction. I want to perform an AND between 0 and 1 instead of 1 and 0, which means that I have applied a 0 over here. If the 0 is applied over here, this value 1 will not get transferred over here, and the value over here will remain 0. Next, I have a 1 input over here. If this transistor's emitter has the value of 0, it doesn't really matter I have a 1 value or 0. Whatever is applied over here, that will be transferred down. So the value over here will remain 0, and this will become a 0 answer. Okay, obviously if both of the values are 0, then nothing happens. This value remains 0, the value transferred is 0, and the result is also 0. So this is the electronic circuit for the AND logic gate. Similarly, the circuit shown over here is the circuit for OR operation. If you can follow the way I showed the input, the key here is that the output is a combination of the value over here, whatever is produced on this line, and the value produced on this line. Okay, so let's very quickly have a look at an input of 1 and 0 and see what result we get. We always have a value 1 over here because it is connected to the power source. Okay, if I apply the value of 1 over here, this 1 will get transferred at this point. So I will get a result of 1. Okay, so not exactly here. This value is transferred on this line here. Okay, so notice that this line is already output is connected to the out here. So it's just a line. So effectively the whatever value is here will start appearing at the output. Okay, so it doesn't really matter what this transistor is performing, whatever is the operation of this transistor, as long as one of the values is 1, we get a 1 over here, which is the operation of AND or 1 or 0 produces the result of 1. Similarly, 0 or 1 will also produce the result of 1, and so on. So the point of showing these two diagrams over here is that the logic gates are actually electronic circuits. They are actually reasonably simple electronic circuits. They're not very complex. Okay, so this means that if all of the computer, which is the case, all of the computer is made of, specifically the CPU is made up of the logic gates, then all of the CPU is actually electronic circuits. Okay, so next we want to see that, okay, the logic operations are simple, and obviously everything in computer cannot just be performed by these very tiny logic operations. We need to combine the logic gates to create relatively complex operations that the computer can perform. So we will look at the arithmetic operations that are possible using logic gates. Here I would like to mention that all of the arithmetic operations, or any operation that the computer can perform, that can be created at the back end in the electronic circuits form using the combination of logic gates. So here, as an example, we will just look at one arithmetic operation, which is add operation, and we will see how add operation can be performed using the combination of logic gates. What is shown here is the circuit for the add operation. Okay, just to recap, what is add operation? We have, if we have an input x, 1 bit, and the second bit y, and the value of x is 1 and the value of y is 1, then adding these two bits will produce a result of 0 in the, just like the decimal numbers, when we reach the value of 9, after that it becomes 0 1. Similarly, in the binary, when we reach the value 1, the next one is 0 and 1. So 1 and 1 added produces the sum result as 0 with 1 as carry. Okay, and because there are no bits over here, so this 1 is our result. So we get, when we add 2 bits with the value of 1, the result of the sum is 0 and the carry is produced, which is 1, and therefore the complete result becomes 1 0, a 2-bit result. Okay, so this is what is being shown over here. There is an input x, 1 bit, an input y, second bit that needs to be added into x, and there is a result sum and a result carry. Okay, notice that there is a carry in here which is also being added into the circuit. Okay, so let's look at this concept of carry in. Look at this example where I am adding 2-bit number x1, x0 with a value of 0 1, And the second number that I am adding is y0, y1, y0, which has the value 1 and 1. Okay, so I'm trying to add number 1 with the number 1, 1, binary number 1 with the binary number 1, 1. Okay, so if we perform this addition, what do we get? Okay, on the first or least significant bit, this C in value will always be 0. Okay, so I'll add 1 into 1. My result is 0 with 1 carry. Okay, so then I add 0 into it, the result remains same. So I have a 0 as S0 output, and my carry goes here. This carry will move up here. Okay, so this is, now I need to add this carry into the two bits x1 and y1, these two bits with a value of 0 and 1 respectively. They also need to add a carry from the previous bit operation. From this operation, whatever carry was produced, that also needs to be added into the bits. So this carry bit is for that specific purpose. Okay, whenever you are performing 2-bit addition, there is a possibility that there was another addition operation before that 2-bit operation, and there is a chance that a carry was produced from that point, and that needs to come up and needs to be added. Okay, so the carry is added, so 1 and 1 produces the result of 0 with a carry of 1. Okay, so that is the purpose of the carry bit. Whenever it is one of the non-least significant bits, there is a possibility that we will have some carry, and that is why we have this C in bit. The circuit is very simple. This is for the purpose of reminder, this is an exclusive OR gate. This is also an exclusive OR gate. And these three gates here are AND gates. This is a simple OR gate. Okay, so let's try to add some of the values and see what our result comes out to be. So notice that this is just single bit operation. The adder circuit can perform, the standard adder circuit can only perform the addition of 2 bits. So let's try to reproduce this specific result and see what do we get. So in this case, x is 1, y is 1, carry is 0 because this is just 1-bit operation and there is nothing before this. Okay, so here exclusive OR of 1 and 1 is being produced. Exclusive OR circuit wants only one of the values to be 1, and then the result will be 1. If more than 1 bits are 1 or all of them are 0, then exclusive OR produces a value of 0. So we will get a 0 as output here, which is becoming input for the next exclusive OR gate. Then this carry bit value of 0 is being forwarded here. This is a 0. Okay, and 0, 0 and 0's exclusive OR also produces the result of 0, which is what we have seen over here. Next, notice that this X is being connected to this AND gate over here. So there will be a value of 1 over here, and similarly this is being connected to this AND gate over here, so another value of 1. All right, the Y bit is being connected here, so this value is 1, and it is also being connected here, so this value is also 1. Finally, the carry bit is being connected here, the carry bit is being connected over here, and that's it. Okay, so 0 and 1 will produce a result of 0. 0 and 1 will produce a result of 0. 1 and 1 will produce a result of 1. And all of these three values are being ORed in to produce the C out output. So OR operation, if any one of these values is 1, we will get the result of 1. So we can see that this value is 1, therefore a value of 1 will be produced over here. So our result will become C equals 1 and S equals 0, which is what we can see over here. Okay, so this is the adder circuit, single bit adder circuit with a carry added into it. Okay, now if we want to add multiple bits like this one, what do we have? We just use the adder circuit that is shown, and we can perform multi-bit operation. So here the first number is a 4-bit number with values of A3, A2, A1 and A0. This is where the bits of the first number will get connected. This is the location where the bits of second number will get connected. We will have our result output as coming up here, and the C in will always be 0. There is nothing before this. Okay, notice how, so here the full circuit is for the time being, ignore the detail of half adder and assume that a full adder exists over here. There's a reason why it is being called half adder, because half adder does not have a carry with it. So this portion can be omitted, but you can replace it with full adder and add a 0-bit, constant 0-bit over here. So notice that the carry produced from first bit operation is being fed as C in for the second bit operation. Similarly, the carry produced by second bit operation is being fed as C in for the third bit, and same is the case for the fourth bit. On the other hand, the carry for the fourth bit is being produced as the result. So adding two 4-bit numbers can produce a 5-bit result, which looks something like this. Okay, so this is a 4-bit adder circuit. If we want to produce a 8-bit adder circuit, we just need to add 8 full adder circuits in the series with the carry from one level being added to the next level, and that will produce the result of addition of 8 bits. Similarly, 32-bit, 64-bit operations can be created. Now, just for a moment, let's look back and see what is this full adder constructed of. It's an electrical circuit consisting of multiple logic gates, as shown over here. So it consists of 6 logic gates. Also remember that it's not necessary that this diagram should be used. There are other ways of producing the adder circuit. If you try to look at internet, you will see that there are multiple ways of producing the adder circuit. Specifically, there is the NAND gate is called universal gate, and most of the circuits are produced in the form of NAND gate. So you will be able to see that representation as well. And these gates are being produced through the electronic circuits. So if eventually the diagram over here will be a complex electronic circuit with the inputs connected to it, with the power connected to its different points. So there will be power supply for this one, this one, and this one. And then here we will have the switches that will connect the input value that is applied to this 4-bit adder circuit. Okay, so all of this is electronics. It's nothing magic. There's nothing that happens out of blue. It's pure electronics. It follows the principles of physics. So in general, if this is what makes the computers, then the computers follow the principles of physics and principles of electricity. Okay, so now we are going to step back from what we have just said, because there will be a relatively bigger transition from this point to the computer side. So we are going to look at the computer components. I'll just give a very high level overview so that we can be ready for the next session. A computer's external view looks something like this. We have a keyboard, we have a mouse, a mouse, we have a printer, probably speakers, a microphone, okay, maybe other peripherals, scanner or something like that. We have a display, and we have a CPU, the computer unit, which is generally referred to in simple terms as CPU, but that's not the CPU only. Okay, so this is what we see in a computer from the outside. It's not necessary that all of these things are present, but this is roughly what we see. Okay, so here these two, the printer and the monitor, are output devices, whereas the mouse and keyboard are input devices. We provide the input from here, whereas from the display, in general, we cannot provide the input unless it is a touch display. Okay, printer is just the output device. We produce the result on the printer. Okay, so these are the in a standard computer. Everything here, these are called peripherals. This is not really a computer. External devices connected to the computer. Okay, the actual computer exists inside this box. So let's have a look at inside this specific box. What do we have inside here? So here is a laptop opened. This when you open a Apple laptop, this is the older Apple laptops, not the newer ones. This is what you see inside. So inside there are multiple things, multiple items over here. For example, there is this portion over here. This is the battery of the computer, okay, and other stuff. But what is important for us in this specific case is that a computer inside consists of a motherboard, which is this this black plate that is up here, this whole thing, and a little bit of this exists under here as well. This portion, all of it is the motherboard. Okay, next, inside on top of the motherboard we have few things mounted. One of them is the CPU. It's the central processing unit, and all the computation in the computer is performed by the CPU. The most important component of the computer is a CPU. Okay, the CPU exists below this fan. This is a fan. Its purpose is to actually cool the CPU. And below the fan, if you take this out, in some of the computers, the CPU is visible right away. In laptops, generally, there is a fan mounted on top of that or a heatsink mounted on top of the CPU. So the CPU exists below this fan. Okay. The second most important component in the computer, without which the computer will not work, is a RAM. Okay, which is shown here. Once again, if you open different computers, the location of the RAM varies slightly and can be installed in a different style. For example, on the desktop computers, it is installed vertically, perpendicularly on top of the motherboard. The final component, which is very important for the operation of the computers can work without a hard drive, but generally it's not a great idea to run a computer without a hard drive. These days, SSDs are very common instead of the hard drives, but the standard term for the storage, permanent storage, is a hard drive. So that is why I'm using the same term. And the hard drive over here is shown here. This is the hard drive of the computer. Okay, so this is the internal view. In this view, the most significant component is CPU. The next component is RAM, and the third component is hard drive. Remember, all the computation is done by the CPU. Everything that we ask the computer to do is actually done by the CPU, and all other components are the supporting components, including the motherboard itself. Motherboard is a supporting component that just provides the connectivity and path between all of these components. Okay, so from next session onwards, we will see what a CPU does. How is it connected with the RAM? What is the purpose of RAM and what is the purpose of hard drive? Why do these things exist in a computer and what do they do? Okay, specifically we'll focus on the CPU and we will try to see what all can be done through the CPU. As a hint, for the purpose of connectivity, the CPU contains the adder circuit as one of the possible circuits that we just saw. Okay, so the adder circuit that we just saw is one of the circuits that exists inside CPU, and there are other circuits that exist in the CPU, and what other circuits exist, that depends upon multiple factors. That is what we will be talking in the next session. So the next session will be about computer operations, specifically CPU operations, and what is the relationship between the operation of the CPU, like this adder circuit, and the instructions of the CPU. Okay, so this is the hardware side, this is the software side. We will see how these two are linked together, what is the relationship between these two, and how we can make the computer perform different tasks. That brings us to the end of this specific session. Thank you for your attention and see you next time.